Hello students, today I'll explain the topic stability of various oxidation states. Okay, so we know oxidation states of D block elements already. So D block elements exhibit different oxidation states, that is a variation in the oxidation states. So those oxidation states stability is explained through various diagrams. So one is Latimer diagram, another one is Frost diagram. So the Latimer diagram was proposed by Wendell Mitchell Latimer. Okay, he is a scientist, American scientist who proposed this diagram. So what the diagram consists of? The diagram mainly consists of oxidation states of the different same element in the particular order. You can see it is a decreasing order of oxidation states. From left to right, the different oxidation states are arranged. Okay, and upon the arrows their reduction potentials are written. So left to right decreasing order means, so left element will have more oxidation state when compared to next element. So you can see +4 oxidation state here and +3 oxidation state, next +2, and it continues up to 0. Okay, next upon these arrows their reduction potentials values are written. That means standard reduction potentials are written on these arrows. So what is a standard reduction potential? So reduction potential is nothing but tendency of an element to undergo reduction. So whenever the element is undergoing reduction is a gain of electrons. So whenever the element is undergoing reduction, there is some potential developed in the potentiometer. Okay, these are the standard potential values of the particular element. So let us see the half cell reactions involved in this Latimer diagram. Okay, if you are taking this diagram, so various reactions are taking place. So in order to convert this Fe2 plus to Fe, okay, Fe2 plus means it requires 2 electrons to convert into Fe. So I added 2 electrons and converted into Fe. It requires this E0 value, okay, minus 0.47 volts. So if Fe3 plus need to be converted into Fe, then so Fe3 plus to Fe conversion requires minus 0.057 volts. Okay. Next, if Fe3 plus, if I add 1 electron, it converts into Fe2 plus. This Fe3 plus can be converted into Fe2 plus by adding 1 electron. That E0 value of this reaction is plus 0.77 volts. Okay. So hence we can take the reaction of FeO4 minus 2. If you add 3 electrons and protons, this reaction actually taking place in the acidic medium. That is the reason we are adding protons, H plus ions. So if converted into Fe3 plus and 4H2O, it requires plus 0.22 volts. Okay, these are the E0 values of the particular reaction. So the standard potential for Fe3 plus to Fe from this diagram, we are getting how much standard potential? 0.057 ohms. But actually if we add both these values, will get 0.30 volts. Okay, so in order to get this value, we need to use the value of delta G0, Gibbs free energy value. So delta G0 equals to minus NFE. Okay, here N indicates number of electrons in the reaction, F indicates Faraday constant, E0 indicates a standard reduction potential. Okay, so let us see this reaction. So Fe3 plus is converting into Fe2 plus. Okay, so this reaction involves 1 electron change. So 1 electron we are adding. So I am multiplying this number into 1 into 0.77 volts. I will get minus 0.77 volts. So minus NFE formula I am substituting. Okay, delta G0 equals to minus 1 electron into 0.77 volts. Okay, 0.77 Faradays. Okay, so next coming to next reaction, Fe2 plus to Fe. Fe2 plus requires 2 electrons to convert into Fe. So if you are substituting this formula in delta G0, we will get 2 electrons change in this. 2 electrons are involved in this change. So minus NFE, minus 2 into minus 0.47 Faradays. We will get plus 0.94 Faradays. So if you are taking the total reaction, so Fe2 plus will be cancelled and Fe3 plus 3 electrons, add to these electrons and get 3 electrons to Fe requires, so if I add both delta G0, I'll get 0.17 Faradays. So this again should be converted into E0. As we are mentioning the values in E0, I should convert this formula into E0. So now by converting delta G0 into E0, delta G0 equals to minus NE0F. Okay, so NF E0, so E0 equals to delta G0 by minus NF. So I'm getting this value delta G naught plus 0.17 Faradays by minus 3F. So I'll get the value minus 0.057 volts. This is the way of getting the electrons, because way of getting the E naught values. If you add directly, we won't get electrons balanced. So we should convert that into delta G naught values, and we should add again. Then only we'll get the actual value of this entire reaction. So E naught, if the E naught value is negative, the reaction will be spontaneous in nature. So the negative sign also indicates that there is a reduction process going on. If it is undergoing reduction, this element can act as a good oxidizing agent. Okay, so if E naught value is positive, the reaction means oxidation reaction, and this substance can, if it is undergoing oxidation, it can reduce other. This acts as a good reducing agent. Okay, so according to this Latimer diagram, the element which is present left side with lowest E naught, that is unstable element. So we told that unstable oxidation means the element which is present on the left side of the series with the lowest E naught, that is unstable according to this diagram. So this is about Latimer diagram.